to me. I misspelled carried and he marked me down a point.
Yes. I love that.
Oh. It's not a carried, it's a borrowed. That's the problem. I don't care about, yeah. That's, I was like,
They spelled communicative wrong.
I had a teacher that would mark us down for elegance points.
Oh my god, I know that.
How elegantly our work was. Yeah.
I'm sorry, I really need to go back to, the one for 3D. Cause
Yeah.
there's this example that I have in my notes that you gave us, where it was like 4 to the power of 12 times 3 to the power of 4, and then you wrote it up like that. And I'm just getting really confused on how to do that. And then also for number 6.
We were really back in school.
Oh, just,
I sure hope we are.
So that example I did is exactly the same work as what's here. What was the example again? From the
4 to the 12 times 3 to the 4, but I'm just trying to use it to understand it better.
yeah. So 4 to the
12
12th
times 3 to the 4.
times 3 to the 4. So how many 12s could I make? 4, because I have this, right? So I have only 4 3s. So they could go with 4 of the 4s to make 4 12s.
You can move past this.
So real quick, no. Are you cool with this? Just this here. 1 3 times 1 2 is 1 6. 2 3s times 2 2s is 2 6s, right?
Yes.
Yeah, is that right? Because this is 3 times 3 times 2 times 2, which is 6 times 6, which is 6 squared. Yeah. So it's all a question about how many 6s can I construct. So how much material do I have? You can look at this as a very physical problem. I got 2 2s, I need 2 3s to make 2 6s. You with me? All right, so if I'm trying to construct 4 beds, how many headboards and how many footboards do I need? 4 and 4, because together they could kind of go with other pieces. So I need equal amounts of pairs for every bed that I want to make, right? Equal amounts of stuff. So if I have 7 5s and I want to make, what do you got, Jeff? I want to make 7 35s. What do I need to make that happen? 7 to the 7th, yeah. Because what would 5 to the 7th times 1 7 be? It wouldn't be this. There's no way I can get 7 35s out of that. I would be 5 to the 6th times 5 times 7. I can make 1 35 out of that, right? Yeah. Okay. So it's just a question of, all right. So real quick, here's kind of where things go a little weird when you're teaching about exponents. So you make a big deal out of the fact that the bases have to be the same, right? In order to add the exponents. But if the powers are the same, you could do something. So if x to the 5th times y to the 5th, I can do something that seems very trivial. I can make it xy to the 5th, right? But that is all I am doing. So if I have 2 to the 5th times 3 to the 5th, that would be 2 times 3 to the 5th, which means I can make 5 6s. That's it. So if I have an extra something, I just kind of put it on the side. If I'm trying to construct 4 beds, then I got 4 headboards and 5 footboards, I'm going to have an extra footboard sitting there, right? You guys gotta look. What's funny is my bed doesn't have a footboard, that's right. So if I have 5 2s and 6 3s, I'm going to have an extra 3, right? Yeah, so if I put 5 2s together with 5 3s, and there's the extra 3, I can then make 5 6s with an extra 3. So it's a very physical idea, constructing numbers from pieces of other numbers. Okay. this might seem like it's just playing around with shit, but it's related to putting factors together in different ways. We're gonna do that actually pretty soon. Factors together in different ways to get other factors. Yeah. Yes?
Last question. So just why is that allowed? Like why is
Which part?
able
Sorry.
to multiply the bases?
Here?
Yeah.
Okay, good.
Any time. Because the example that I asked is because you make any use.
Alright, you ready? Okay. If I did this, wouldn't this be 5 of these? Why did I pick 5? You with me? That's what a fifth power means. Now I'm just multiplying, correct? I can multiply whatever the hell order I want to. So I'm gonna multiply all the x's together. So I get x to the 5th, right? I'm gonna multiply all the y's together, I get y to the 5th. So these two things are the same then. Yeah. So it's real quick, this is so awesome. Okay, and you're all like, jury's out on that. Okay, hold on. This is gonna be silly. What can I do here? What am I allowed to do here? Distribute, correct? And it's why is that true? Because what is multiplication based on? Most fundamentally, multiplication is repeated. So multiplication is based on addition. And this is added. Therefore, they should play well together. 4 times x, 4 times 2y, whoop-de-doo. Now, what are exponents based on? Are these multiplying? Yes, this should play well together. This is called, not surprisingly, exponential distribution or power distribution. It's the same thing as this kind of distribution. I'm just distributing the power to both. They are both being raised to a 5th power. You guys, semi with me? Okay. Some of you guys look upset or something? Okay. Yes?
What about
1D. Oh, what was the thing about 99? Why was 99 special? What can you do with it? A little 99. 99 times, I'm just going to do a different one. 41. Just because. Go ahead.
So basically the first two numbers of the thing is going to be basically just words. One less, so it'd be like in this case it'd be 40, and then the other two numbers would be how much is left in that 41 to make 100.
Sure. And what that's a shortcut to is this. Everything you said is beautiful.
Okay.
But it's kind of a shortcut to this. 99 is 100 minus 1. Is that cool? So that would be 4100 minus 41. Do you see how, I don't care what the number is here, aren't I always going to be subtracting it? And it's going to be subtracting from some hundreds, right? So you start to see why the shortcut. So watch. 1 less than this. Why? Because 4100 minus 41 is 4,000 something. And what is that, of course? $1 minus 41 cents?
59?
Yes, 50. So a shortcut is, whenever you multiply by 99, it's 1 less than this, and then 100 minus this. I am nothing wrong with that. The more we rely on shortcuts, the more we lose touch with why the shortcuts work. And then our foundation that we build other math ideas on is shaky, right? And that's why a lot of my students, I have a lot of little mini rants about stuff. Like the FOIL method, I don't think should exist. A lot of things, I'm sorry. And it's because it takes us away from the actually easier, more basic reason why that works. Okay, enough of that. You're all like, whatever your philosophy is going to for you. So that's how you do that problem. It's one way. You could do the shortcut, that's fine. Okay. All right, guys. Let's put those away. You guys can work on those corrections. They're due the day of the next test, which I currently have no idea when that's happening, but you know better
If it's
than I
gonna
do.
happen. No more tests for the rest of the year.
Take your time.
End of this month.
I should do it.
You don't want that.
We made
Trust
it
me.
to the end of this month.
Prioritize your mental health.
Yeah, mental health, no more tests.
And no more homework either.
Make it June 1st.
It's just take pictures
No,
of the
it's
note
set.
and give-
It's on your homework sheet. I'm not saying I don't know when it is. I put it on a paper, so it doesn't have to be in here. So you know when the next test is. Okay. Let me start off getting into chapter 5 just by asking you guys a question. What's a prime number?
other than
Sure.
yourself and
Be a little more specific. Another number, what do you mean? By any other number? The only numbers divisible by is, the only numbers
Full.
are itself and 1. Because 1, of course, goes into any damn thing. 1's very easy going. Thank you. You guys kind of, so everybody kind of knows what a prime number is. Can you start telling me some prime numbers?
1, 3, 5.
No, now here's the neat thing. 1 is not prime
Wait, why not?
because it's officially only divisible by 1. It's gonna be,
Oh, it's
so we call it the unit number. So it's its own special little category. So what is the first prime number?
2.
2. I like that. Every other prime except 2 is going to be what kind of number? It's got to be odd, because if it's even, it's divisible by 2 then, right? 2 is prime, because great, it's divisible by 2, but that's it. That and 1, so it's officially a prime number. So 2,
3,
3,
5,
5,
7.
7. So far, 11. Okay, that's weird. Yes. 13. 17.
17's weird.
17's weird. I agree. Anyway, it goes on forever. One thing we know is that the primes go on forever. We know that's true. That's been proven. If you wanted to, and you know, I know you do, you aspire to this. If you wanted to be like the next mathematical icon for all math people to kind of bow before, if you could figure out a pattern to the prime numbers so that you could predict the next one, that would just blow everybody's brains, right? They would all be like, they would all love you and hate you at the same time, because there's a bunch of people working on that right now, and we haven't found a pattern to the prime numbers yet. Think about that for a second. Do you see what I'm saying? It felt like there might be a pattern on the first few, but then eventually it gets really weird. There are some primes that are separated by 2, right? Like 3 and 5 and 7 and 11 and 13. And then you got some that are separated by 4. Sometimes they're separated by 6. Kind of with me? There are primes that are in a very specific form. So tell me again. One thing you can tell me that's true about every prime except 2, of course, is odd. So isn't every odd number... All right, watch this. What kind of number is that? 2 to some natural number. Is that an odd number or an even number? Even, definitely. 2 times 2 times 2 times 2. If I do that, whatever number of times is going to be even, correct? So if I do this, what kind of number is that? Odd. So there are some prime numbers that are in this form. And they're called the Mersane's primes, named after Fred Mersane. Oh, forget his first name. Somebody who did this theorem. So one thing we look for are these kind of prime numbers. So we have supercomputers just chunking away on figuring out what the next largest prime number is. So believe it or not, every few months they're like, we found the next biggest prime, and there's a little subset of people that are like, oh, okay, you know, and everybody else is like, what's happening? Are you guys semi with me? So you all knew a little bit about primes. You had no idea there are people that are obsessing about primes, and there are.
If it exists.
There was a computer program that would run in the background back in the day when we had screensavers. And I had it installed on my computer, and it would search for the next largest prime. And if you found one, you would get a little something from them. Hey, or this month's winner is Jeff. Yay. My computer never found one. I'm like, stupid computer. Anyway.
So Bitcoin mining, but worse.
Huh? Yes.
Or Bitcoin mining, but
Yes.
worse.
Bitcoin mining, but with no real goal. Okay. no monetary reward. So what do you call a number that's not prime?
Even.
No, because 2 is not prime. 2 is prime. They're called composite numbers. So composite numbers, this name kind of makes sense because a composite number is composed of more than just 1 times itself. Okay, so we're going to get into stuff like least common multiple, greatest common factor. Remember making prime factor trees?
Yes.
Yes. Somebody likes that. Love it. Okay. Okay. So part of what we're going to also do is we're going to get into something that I kind of introduced to you guys earlier. How to tell if a number is divisible by 2, 3, 4, 5, 6, 8, 9, maybe 11. We'll see. Okay. So real quick, composite numbers, of course. For example, 18. What are the factors of 18?
3 and 6.
1,
8,
2,
3,
3,
6,
4, 6. There you go.
I was saying 6.
I know. I just wanted to see, make sure everybody was with me.
9.
9. All right. Now, real quick. And then, of course, 18. Does everybody agree there's a point that you sort of can stop thinking because 6 goes with 3, 9 goes with 2, 18 goes with 1? I think I already told you guys. Did I tell you about this?
Yeah.
I remember watching a video where the girl was doing this. Do you remember how to figure out what that turnaround point is?
What
No.
does the word say?
Say again?
Composite.
The word is what numbers?
Composite, yes.
So that's an O.
Yes.
That is a no.
Composite.
He's obviously an English
Composite,
teacher.
yes.
Composite numbers.
It's a lot like compost, is composed of a lot of different elements. If you have a compost pile, composite numbers are numbers composed of a lot of different factors, or at least more than 2. Now, real quick,
What's the trick again?
yes, what's the square root of 18 close to?
9.
It's just the square root of 18. What's this number I can square root that's close to 18? Below 18?
Oh, 16.
16. So the square root of 18 is around 4 or something, right?
Yeah.
So the minute I get to 4, then I can start turning around. Now 4 might not be an answer, but that's really kind of cool. So if I wanted to factor, what do you got, Jeff? You can do it. 48. What's the square root of 48 roughly?
Shoot.
It's gonna be 7 something.
Just below 7.
Yeah.
So the minute I get up to 6, I can sort of stop thinking so hard. Right, so what goes into 48? 1, 2. Oh shit.
4. 3. Wait.
4, 6. Now, square root of 48 was about 7. Now I turn around. Now I start saying 6 times what? 8. 4 times what? 12. 3 times what? 16. 2 times what? 24 and 40. Okay. Is that kind of cool?
Yeah, that is very cool, actually.
Yeah. So the first half of the list, you have to really kind of think. The 3 got us on that one. I don't know if you guys, real quick, a couple things about this specifically.
How did you get 12 with 6 times 8?
Sorry?
Where's your 6 times 8?
Right here, 6 times 8.
Which is 48.
Yeah.
That would be a lot harder with a bigger number, though.
How do you mean? Well, yeah, the bigger the number, the longer the list might be. You're right.
No, like finding out. Like,
Oh, yeah. Then you're just doing the calculator. All right.
I'm sure some calculators have to pick how many factors a number has.
Oh, no. Is everybody with me so far? And again, that's just a cool little thing to know about how numbers work. And so if I have a perfect square, this is kind of cool. Square root of 36 is 6. So 6 is going to be the middle point. It's the middle point, so now I build around it. Because 6 times 6 is 36, it's itself. And then I could go 4 times 9, blah, blah, blah. Something else I want to say about 48. So, watch this. What do you got, John? 12 times 4 is 48, correct? It's ground shape. I know. I'm going to write a paper about it. Watch this. This is kind of cool. Isn't 12 3 times 4? And what's 4 times 4? 16. So 3 times 16 is also 48. So this is what I was saying earlier about putting things together. The idea of taking a factor you know and just playing with the factors of those numbers, and then you can create another set of a couple of things that work. You guys kind of follow what I'm saying? This is a really useful tool to use. Does anyone remember factoring polynomials?
Yes.
Yeah, figure out two numbers that add to be something and multiply to be something. You guys
I
remember
hated
that?
those. I found a calculator for that.
If you knew about this, that's a little bit quicker, because sometimes you get these funky ass things. When I say 48, 3 times 16 is not the first thing that comes to mind, correct? Okay. No reaction. Okay, there. It's not the first thing that comes to my mind. Okay. Alright. So this kind of, I might as well do this, we're sort of headed that direction, but just to remember, let me tell you this, a couple things. Knowing where the list turns, doing the square root trick, is good to know. Wouldn't it also be fantastic to know how long the list is going to be?
Yeah.
Wouldn't that be kind of cool? To make sure you didn't miss anybody? So let's take 48. Can I make a prime factor tree out of this?
Probably 24 to.
Yeah, it doesn't matter where you start. We're all going to end up in the same place. So if you saw 24 times 2, I can just keep doing 2's, right?
Yeah, 2 times
12 times 2,
3 times
6 times 2, 3 times 2. Okay. So you make this little weird ass Christmas tree with the little ornaments. What's a nice compact way to write that? 3 times 2 to the 4. So are you with me? Alright, we're gonna get into some slightly funky territory. If I want to construct numbers that go into 48, would you all agree with me that I can just combine any number of 2's and any number of 3's up to 1, up to 4? So for example, if I take 1 3 and 2 2's, what's that? 3 times 2 squared? 12. And of course it's a factor of 48 because I made it out of pieces of 48. You guys with me still? Or, hopefully you were with me. You're still with me. Okay, all right. Does it make sense? Okay. Okay, but if all of these go into 48, then any multiplication of these also goes into 48.
Oh, okay.
Right?
Yeah,
If
yeah.
2 goes into 48, 4 times, then 4 also goes into 48. Any combination of those goes into 48. Are you guys with me? So if only there was a quick way to tell how many freaking combinations there are, I could tell how long the list was going to be. Yes?
I had a question. Would you have to add the 3? Like in this example?
No.
So
Yeah,
it could just
so
be 4
I could do 2 cubed.
Okay.
What's that?
12, 16.
8. And does 8 go into 48? Yes. So
Okay.
any combination of any number of these, up to 4 2's, up to 1 3. So what about no 3's times no 2's? Is that a factor of 48? Yes. 1 is a factor of everything. Okay. Is everybody roughly with me? Here's where things get nitty. Okay. Like you just said. You see, stay with me. It's going to get a little weird. I'm going to show you a shortcut. Okay. Just like you just said. Couldn't I take no 3's times no 2's, right? And that's 1 times 1. Isn't 3 to the 0, 1? So like it just did, 1 times 1 is 1, and of course 1 is a factor of everything, right? Then could I then take no 3's times 1 2?
Yeah.
What's that? 2. That's crazy. No 3's times 2 2's. Do you guys see what I'm doing? No 3's times, sorry?
Couldn't you take like a 7 and put it to the 0 power times 2 to the second?
True, but yeah, I mean technically that would work, but I'm trying to live within the idea of I can take any number of 3's up to 1. So I can take no 3's, or I can take 1 3. I can take no 2's, I can take 1 2, 2 2's, 3 2's, 4 2's, because that's the most I can do. Does that make sense? So 1 3 times 4 2s is 48, and of course 48 is a factor of 48. Okay. All right, and now I understand. Stay with me. This is so cool. Okay. Good Lord, this sucks. And can you imagine if I made this bigger? This idea of making this list of how many things would suck. But here's the shortcut. Here's the shortcut. How many options do I have for the 3? It could either be 3 to the 0 or 3 to the 1st. Is that cool?
Yeah.
How many options do I have for the 2? 2 to the 0, 2 to the 1st, 2 squared, 2 cubed, 2 to the 4th. So how many options do I have? 5 options.
Okay.
I have 2 options for the 3. 5 options for the 2. 5 times 2, I have 10 total things I can make. And let me see, I shouldn't have erased it, but the list of factors was 1, 2, 3, 4, 6, 8, 12, 16. Why did you put it way up here, Jeff? How long is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10! Damn straight. So, real quick. I appreciate that. Stay with me now. So all that was, every time so again, the basic idea is, if I take at most 1 3, so I can take no 3s or 1 3, and then up to 4 2s, right? If I do any combination of those, I get a number that goes into 48. All this does is it tells me how many combinations I can make. I have 2 options for the 3, 5 options for the 2. That makes 10 total options I can make. So, let's try a fresh problem. What about 60? Can you guys take a minute and figure out the prime factor tree for 60?
More like I like mustard.
Huh? You like mustard?
No, must we?
Oh, must you? Okay.
Got it.
Oh,
Yeah, I love this mustard.
Mustard's
Yeah, man.
that's such a weird
I brush
non
my teeth
sequitur.
with it.
I hate mustard so much. It is
You
so-
don't like mustard?
It's nasty.
All right,
You
guys.
do seem like a ketchup
Guys,
boy.
real quick. Guys. I know I started that. I'm also going to end it. Now, take a minute. Prime factor 60, please. Make a prime factor tree. Brittany's like ketchup. Everybody else, I'm done with this shit.
Done with the mustard ketchup.
Yeah.
I guess
So I haven't said this yet, but I did say this part. I don't care how you start, we're all going to end up in the same place. Correct?
Yeah.
There's a billion, not a billion. There's a few different ways I can start. So if I do 6 times 10, that might not be the way you guys started. 6, of course, is 2 times 3. That's crazy, Jeff. 10 is 2 times 5. So I get 2 squared times 3 times 5. Is that cool? I call this, because I am weird, I call this the DNA of 60.
So,
Because if you put that together, you're going to get 60. You're not going to get anything else. Go ahead.
I did 2 times 30.
Say again.
Is that an acceptable?
Yeah, no, it's fine.
The same.
So if you do 2 times 30, keep going. What's 30?
15 times 2.
3 times,
No, 15 times
oh, 15 times 2, I'm with you. And what's 15?
3 times 5.
So what'd you get? How many 2s?
2.
Squared times 3 times 5. Same thing I got, right? So again, why does it not matter? If I take a car apart, and I start with the wheels, but I take it all apart, and somebody else takes a car apart, but they start with the steering wheel, are we going to end up with all the same parts? Yeah, if we take it all the way down, we're going to end up with the same damn parts of the freaking thing. You guys with me? Okay? That's all this is. We're going to end up in the same place, because I don't care where you start, the 60s had to have the same components. Now, here's the shortcut to what I just did over there. I could have 2 to the 0, 2 to the 1st, 2 squared. So whatever the power is, you do one more than it. 3 times, what's the power on these? 3 times 2, one more than it, right? Times 2. So how long would the list of factors be for 60? 12. If I made a list of factors for 60, which we're going to do right now, it would be 12 long. That's what that means. If I break down into prime factors, I really want you to understand this. Let me do this one more time.
Oh, okay.
The long ass way to do this would be, I can have no 2s, no 3s, and no 5s, correct? Or I can have 1 2, no 3s, no 5s. Or I can have 2 2s, no 3s, no 5s, correct?
You
Why is
messed
that a thing? I love that, Jeff. Good job, buddy. Okay. Is everybody with me? And then I could do it again. Now I could have no 2s, 1 3, blah blah. You guys kind of with me? Do y'all see that there's 1 2 3 options for how many 2s I can have? There's going to be 1 2 options, either 0 3s or 1 3. And there's going to be 2 options for the 5. So the shortcut is the options for each is 1 more than the power. And if I multiply those together, it tells me how many total options there are to put them together to make a number. So, for example, one specific way to make a number here is, bless you, 1 2, no 3s, and 1 5. Is this a factor of 60? Yes. So all this number means is how many ways can you do that and get distinct numbers? That's all that means. So, if I combine the two things we just did, what is the square root of 60, roughly? It's really close to what number that I can do the square root of? What's the square root of 64? 8. Yes? So therefore, I know when I'm making a list of factors of 60, when I get to around 8, that should be where I kind of start turning around and just making pairs. You guys with me? And I know now that I'm going to have 12 numbers here. So if I do 1, 2, 3, 4, 5, 6, 7 doesn't work, 8 doesn't work, and that's the turnaround point. So now I can just do 10, you with me? 12. That's where it gets interesting. 4 times what? Nope. So it's 5 times 12, which is 5 times 3 times 4, which is 15 times 4. Yes? So 4 times 15, 3 times 20, 2 times 30, 1 times 60. How do I know I didn't miss any? Because it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, frickin' 12. Yes? And 4 would be an easy one to miss, because we don't think 4 times 15 is 60. We don't think that. Even though a quarter of an hour is 15 minutes. So we actually do know it, it's just not on the tip of our brain, right? You guys with me? Thank you, Babylonians. Okay. Okay. All right, so those are 2 nifty little things. But not only are they nifty, you have to know how to do them, right? So if you don't think they're nifty, you still have to know how to do them. So it's the square root thing to know where the turnaround point is. Does everybody know what I mean by turnaround point? So that was a turnaround point where I could just start pairing up these numbers with their what multiplies B60. And then I could do this to figure out how long the list is supposed to be, so I know if I missed it. Okay. All right. I like it. What's up? Oh, I know. She got most of it done early. It's good. Okay.
What are the names for these things, like the actual names?
Say again?
Like the actual terminology for the things that you're talking about? Or they don't have terminology?
They really don't. This book might call them something. I mean, there's prime factor tree, of course.
Wait, sounds legit.
Here's something interesting that I always forget. Remember when I called it the DNA of a number? That's called the fundamental theorem of arithmetic. Is the fact that every single number can be expressed as a product of primes in its own unique way.
Boring.
Okay, thanks for the immediate Yelp review on that. Let's see, okay. So I want you guys to, everything we just did, let's do it for this number. What do you got, Jeff? 42. The answer to life, the universe. how long the list would be. You know, make a prime factor sheet, how long this would be. Figure out where the turnaround point would be, and then make the list. So basically, analyze the hell out of 42. Did everybody get their test back? Okay. Pretty basic. Poor little dude. What are you guys getting for the prime factor tree?
2 and 21.
Alright, 2 times 21, sure.
7.
And then 3 times 7, 11. So 2 times 3 times 7. So what's the main thing you're looking at to figure out how long the list should be? How many of each? The powers of each, right?
So there's 2 0, 2 1.
Yeah, so the power here is 1, so there's 2 options for 2, 2 options for 3, 2 options for 7. Now really, because I could either be 2 to the 0, so since the one option is back to the 0 power, that's why there's always one more than it actually says. That's
Where
why
are
they
the
add
2
one.
options for 7? I'm sorry.
7 to the 0, 7 to the first. So each one of them. So if I had like 5 to the 7th in something, then it could be 5 to the 0, 5 to the first, all the way to 5 to the 7th. That would be 1 to whatever is 8. So the shortcut is you just add 1 to this. I like it. 2 times 2 times 2. Crazy enough is 8. What's the square root of 42 roughly? 6.
7.
Between 6 and 7, right?
4, 9.
So if I start to make this list, I know it's supposed to have 8 things in it, and I know I should turn around somewhere around between 6, so around 6. So it'll be 1, 2, 3, 6, 7, 14. Yeah, 14, you're right, I'm sorry. 21, 42. All right. Too close to it. So did we end up with the right number of things? Yes, cool. Okay.
That's pretty crazy.
Can you just go back to the 2 times 2 times 2? What do you mean by options?
Okay. So it could be no 2s, no 3s, no 7s. So 1 is a factor of 42, correct? It could be 1, 2, no 3s, no 7s. And 2 is a factor of 42, right? Okay. Could I do 2 squared? No, because the most I got is 1, right? The most 2s I got is 1. Okay. So so how many things can go in the first place? 2 things, 2 to the 0 or 2 to the first. How many things can go in the second place? 2 things, 3 to the 0 or 3 to the first. How about the third place? 2 things, 7 to the 0, 7 to the first, right? Now real quick, for every option for the 7, there's 2 options for the 3, and for every one of those, there's 2 options for the 2. So how many total options? 2 times 2 times 2. Sort of like, real quick, if I had 3 colors for the outside of a car, and 4 colors for the inside of a car, Y'all with me? I'm trying to buy a car, so maybe I can pick a silver, blue, green, whatever the shit. Inside could be tan, whatever. I don't know. You guys all with me? Somebody likes tan somewhere. How many total combinations of cars can I make, color-wise? Shortcut is 12. So every 3 options for outside color, there are 4 options for inside color.
Oh no, probability trees.
How many does that end up with? 12.
What do you call that thing you just drew?
A tree.
Like probability.
Yeah, it just is a tree. It could be a probability tree. In this case, it's not really a probability tree, but
Will you ask this to Robin?
no. But I'm just doing it for another visual. Right? Some of you guys might have seen these before.
I like it.
These are called, in general, they're called decision trees because every branching off point is a decision I can make. So the first decision is the outside color. There's 3 options, and for every one of those, there's 4 options for the inside. Do you see how that leads to multiplication? For every one of these, there's 4 of those. And there's 3 of these, so there's 3 times 4 total. Yes. Which is why this works. Okay, I like it. Kick ass. Okay. Okay, so,
Is this all in chapter 5?
totally. We're on the second page of section 5.1, basically. Yeah, this was jam-packed.
And there's only 2 chapters in chapter
2
5.
sections, yeah. Okay.
It's only 12.
Oh, man.
So they had to cram it. All right. Okay. So again, it's all about practice. It's all about asking follow-up questions if it doesn't make immediate sense. You're not used to looking at stuff like this. You're not used to it. So of course it's not going to make immediate sense, but hopefully it makes enough sense that you can kind of build on that. Now, I want to introduce a symbol that represents the word divides, right? So would you say that 7 divides 21? That's a very strange way to say this. But what do you think that would represent? Does 7 divide 21? Yes. Why does 7 divide 21? Yeah. And what's a very quick way to answer that question? Why does 7 divide 21? Because 7 times 3 is 21. There's a number that exists that 7 multiplied by it becomes 21. That's why 7 divides 21. Is that cool? So this symbol, that symbol means divides. So if I write this, what does that mean? If I say that's true, A divides B,
A divides B.
what does that mean? Must exist.
A tree.
There's a number that exists.
Yeah, a number like 3, does it have to be 3? Could be anything. So what do we could call it? Yeah, we could call it C. Well, let's call it either like N, right? We kind of use N for our number that represents any natural number. There must be a number A times N equals B. Alright, so that's just notation, right? You guys know what it means for a number to divide into another number, so this is just kind of notation for that. I like it. So is it true, does 6 divide 15? Nope.
No.
This is not a whole number that I can multiply 6 by to make 15, so we do this. Ha!
So,
We
but
actually
this
just
would
do
only
that.
be for whole numbers, correct?
Yes, exactly. So we haven't talked about fractions yet.
Right.
So when I say 7 does not divide into 22, we know it does, but not evenly. So we inherently, when we say divides, we mean a whole number, right?
So that would be like the remainder kind of thing?
Yeah, 7 does not divide 22 because there would have to be a remainder, which we could write as a fraction, we could write as a decimal, right? Okay, which is in our future. Okay. Now we get to the cool shit. Okay. Let me see if you guys remember this. I'm almost certain I told you this. How can I tell if 2 is easy. How do I tell if a number is divisible by 2? It just has to be even. Yes? If I have an even number, then 2 goes into it. That's by definition, basically, right? Yeah. So not very exciting. How can I tell if a number is divisible by 3? I heard something.
The last numbers are the 3 and 6 are
Yeah, if I have a number where all the numbers add up to be, oh shit, let me see. Sure. Alright. If all the digits of the number add up to be a multiple of 3, that means the whole thing is divisible by 3. What do these digits add up to be? 9. So is this divisible by 3? Yes. Does somebody have a calculator? Can you tell me what this is?
3807.
3807? That's kind of beautiful. The rule for 3 is if all the digits add up to be 3, then it's, a multiple of 3, then it's divisible by 3.
Is that the same for all numbers?
Huh?
Is that like the same for like all numbers?
Yes.
Okay.
Yes. I don't care how big the number gets, small the number gets, it's true. I like it. Of course, we're talking about whole numbers. Huh?
But isn't that divisible by 3?
Yeah, let's see. What do these add up to be? 18. Yeah.
Yeah.
So this is also divisible by 3. What would the answer to that be?
1,260.
Yeah. What do those add up to be? Kids. Why did I get all greedy? 18. Is this divisible by 3? Yes. What does this stop? It doesn't. Then when I divide that by 3, I get 423, I believe. I didn't do this on purpose, but I completely made the ship out of nowhere. I wish you could take credit for this. Now I'm curious where it's going to stop. So that'll be 141, is that right?
That's 6.
That's 6, everybody.
I don't think it does stop.
Divided by 3.
I don't know.
47. What's 4 plus 7, right? Isn't it 47?
Yes, 47.
47, oh man.
Oh.
And that's it.
That's it. Too bad, everybody.
Oh, so this is
Real quick, okay. Now, let me see, real quick. I'm gonna show you, all right, maybe I'll do this for 9. 9's a little easier, yeah. All right, so that's the rule for 3. Now, real quick, the rule for 9, doesn't it make sense it should be connected to the rule for 3 somehow, because 3 times 3 is 9? This is all about divisibility. So thankfully, the rule for 9 is the same as the rule for 3, if you're careful. Any number that adds up to be, all the digits add up to be multiple of 9 is divisible by 9. You guys all with me? So for example, on this level, 1 plus 4 plus 1 was 6. That's a multiple of 3, correct? But is it a multiple of 9? No, so 9 would not go into 141. Which is why that was not divisible by 3 again. The original problem, 1 plus 1 plus 4 plus 2 plus 1 was 9. And that's divisible by 9. That's why 3 went into it twice. 1 plus 2 plus 6 plus 9, 18. That's a multiple of 9. That's why 3 went into it twice. You guys, let me stop for a minute. You guys all with me?
And then when there was only 1, that's why there was a million.
Yes. Okay. Now, let me see if you guys are. Is everybody so far so cool? That's so awesome. The rule for 3 is the same as the rule for 9. Just gotta be careful. The rule for 3 is if the digits add up to be a multiple of 3, 3 goes in. If the digits add up to be a multiple of 9, 9 goes in. So 9 certainly doesn't go into every number that 3 goes into. Of course it doesn't. 6 is a great example. You guys all with me? Okay. Not every rule for every number is that though, right? Because 4 is not related to 3 in any nice way, multiplicatively, correct? So the rule for 4 is not going to be anything like the rule for 3. Okay. Before we get to the rule for 4, I want to look at 9 real quick. Let's look at a 2-digit number. It doesn't really matter, but we'll start. Well, let's do a 3-digit number. Yeah. So I'm doing this sort of like that bonus question. A, B, C would, if it was A is 3, B is 2, and C is 1, that's the number 321. Are you guys with me? This is not A times B times C, it's A, B, C, the digits. So A plus B plus C is a multiple of 9, let's say, right? How do I know if it's divisible by 9? If I add up the digits and it's a multiple of 9. Are you guys with me? Yes?
Being like super easy about it, so we could just put 800 and more.
Oh, yeah. So A could be 8, B could be 0, C could be 1. 801. Yeah. But I want to do it for every possible 3-digit number. Yeah. So I got to use the letters. Yeah.
Okay.
Does it make sense?
Yeah.
Okay. Yes.
Does like the 3 rule work for 6 as well?
We'll get to 6.
Okay.
Okay.
So I'll take that.
3 is in 6, but so is 2, so they work together. So we'll see. Let me see if you guys are cool with it. This is going to be a little freaky. Stay with me. ABC, isn't that A times 100 plus B times 10 plus C? Yes? If it was 801, wouldn't that be 8 times 100 plus 0 tens plus 1 1? Yes? Okay. So you guys are all with me. Say again? That's okay. Again, okay, stay with me. This is weird as shit. I just want to show you this because I am insane. Just go with me. Okay. Is everybody semi-cool with this? If it was 726, 7 times 100 plus 2 times, that's all it's saying, correct? And I'm also throwing in there the fact that we know it's divisible by 9, which means when I add up all 3 of these, I get a multiple of 9. Is that cool? Now, cool. This is so freaking cool. So let me write this a little better. Isn't this 100A plus 10B plus C? Yes? You're like, yes, Jeff, that's so much better. No. Now watch this. This is so cool. All right, just watch. Isn't this 99A plus A? Doesn't it make 100A?
Yeah.
Okay. 9B plus B makes 10B. And then plus C. I left a little too much room, but that's okay. You guys all agreeing with me that that's the same as that? 99A plus A is 100A. 9B plus B is 10B. Just sound like my 5th puberty. Alright, so anyway, does everybody agree that this is divisible by 9? Whatever the shit it is, it's divisible by 9, correct?
11 and 1.
Because 9 goes into 9 and 9 goes into 9, yes? Is this divisible by 9? Yes! So is the whole frickin' thing divisible by 9? Yes. That is a proof of the divisibility rule for 9, which is nothing you ever have to do. But I just wanted to show it to you at least once. Because I'm sure somebody out there is like, why the shit does this work?
You'd be
I
like, wow,
felt
looky
that-
here.
Say, yeah, exactly.
If A plus B plus C is divisible by 9,
Yes.
technically wouldn't that be like, say, 1? Because it's like 1A plus 1B plus 1C, so that'd be like 1/9, and now we're going into decimals.
Wait, what? No.
Yeah, that's.
So A plus B plus C could be 18. It's just some multiple of 9, right? That's what that means. It's some multiple of 9. Whatever
It's
A,
like how you're combining like terms with the 99A plus 9B plus 1A plus 1B plus 1C.
sure.
And so if I'm like thinking about like 1A and then you're dividing it by 9, that would be.
Oh, no, but this whole number. So the question is this number divisible by 9 if I know that the digits add up to be a multiple of 9? That's the question, right? You with me? So I'm assuming this is true, and I'm rewriting this number so I can work with it. Now, so if I take, so whatever digit this is, I rewrote it like this. Correct?
Yep.
So now if I try to divide it by 9, will it work? Yes, because 99A is divisible by 9. Agreed?
Correct.
9B is divisible by 9. A plus B plus C, whatever shit number that is divisible by 9 by assumption. I'm assuming that all the digits add up to be a multiple of 9. And I'm showing that that assumption means the whole number is divisible by 9.
Is that what the M is? Like,
Yeah.
Okay.
It's like 9 times 1 or 9 times 2.
Can we do this with like an actual number maybe? Instead of
Yeah, we did. So, all right. Not all these steps. I wouldn't need all these steps. So, like,
9 ones.
846, right? Okay. So let's do this. So 846. That would be. I'm going to overdo this. 8 times 100 plus 4 times 10 plus 6 times 1. Yes. You guys with me? So that would be 99 times 8 plus 8. Is that okay? So read with me. That I just took this. That's 108. So it's 99 eighths and an extra 8. 9 fours and an extra 4. Yes. And then I got a 6. Is that okay? All right. Is this all divisible by 9? Yes. 8 plus 4 plus 6 is, and is that divisible by 9? Yes. So the whole number is divisible by 9 if the digits add up to be 9. It is this that I just did. Is that anything you ever have to do? No. Does everybody understand? Sometimes I feel like students don't understand when I'm trying to drive why something works versus showing you what you have to do. So here's what you would have to do for this kind of problem. Jeff?
I just want to know if it's the same, like, proof for 3.
Yeah, it's similar, yes. Be careful what you mentioned. So if I said, is 846 divisible by 9? Or I could just say this, does 9 divide 846? Question mark. All you have to do is 8 plus 4 plus 6 equals 18 equals 9 times 2. Check. Next problem, Jeff. Right? That's all you have to do, correct? Everything else I've been doing is just why does that work? Okay. I like it. That's where I get in the most trouble as a math teacher. It's because I try to show students why it works, and that drives them a little crazy. And some students think, am I going to have to do this? No. So, in a lot of my math classes, I'm like, we're still in the derivation phase. I'll say that every 5 minutes or so. We're still deriving. So we're still proving. So what about, so we got the rule for 2. We got the rule for 3. What about the rule for 4? We also got the rule for 9 as a preview. What about the rule for 4? Does anyone know a divisibility rule for 4 already?
Is it something to do with 100?
Yes.
Since it's the
4 goes
last-
into
the
100,
last two
correct?
numbers.
So 4 divides 100. So doesn't 4 divide 100 plus any multiple of 4? You guys all with me? If 4 goes into 100, then it must go into 112, because it goes into 112. Yes? What that means is, I don't give a shit how big the number is. I'm just going to start writing numbers as they come to my mind. Here I am, just writing freaking numbers. Damn, Jeff, that's enough shit. Please stop. Okay. I know that's divisible by 4 because the last 2 digits are divisible by 4. That's all I need. Because if 4 goes into 112, doesn't go into 212? Yeah. If 4 goes into 100, it goes into 200. It goes into 300. It goes into 3,700. It goes into 3 billion. 3 billion? It goes into anything that ends in 0, 0. Therefore, it goes into anything that ends in a multiple of 4, the last 2 digits. I don't know if you guys are really with me. So, does anyone think they ever heard this before? Okay, one of you guys. Okay. This is good shit to know. I know that calculators exist. But we're humans. We made numbers up. We should own them. We own them, right? It's only good for things that can't feel, okay? Numbers, okay. You guys all with me? So we should know exactly how the hell they work. You should be a little upset if you feel like you've never been told any of these things. You really should be. I'm not going to ask you to put that calculator. I don't know if your calculator can handle this. I mean, if I just do this, all right. That's divisible by 4, yes? Somebody do that real quick for me in the calculator. What is that? Don't try to do it, Jeff. I'm not going to look at it.
Do it.
No.
Do it.
Do it. Do it.
Do it. I think it's like a fact check you.
I'm old and I don't care about peer pressure.
Oh,
man.
man. 177879490.
177879490.
Damn.
Is that right? It's almost like I'm doing numbers.
I don't know you're doing
How many
memorization.
did you add to that?
Is that divisible by 4?
Yeah.
No. Is 90 divisible by 4? No. Quick way to tell is 4 goes into 80, correct?
Yeah.
Does 4 go into 10? Nope, so 4 can't go into 90 because it's 80 plus 10.
It's divisible by 2 though.
It's divisible by 2, totally. Okay. So now we got a rule for 2, it's got to be even. Rule for 3, digits add to a multiple of 3. Rule for 4, last 2 digits divisible by 4, correct? Rule for 5 is easy as shit. What's the rule for 5?
5 or 0.
Ends in a 5 or a 0. Kick ass.
Yes.
Thank you, 5. Thank you, 5.
Good 5.
High five.
Yeah, that's why 5 is part of a high 5. That's the reason. 6. Somebody brought up 6. 6 is interesting. In order to be divisible by 6, I must be divisible by 2 and 3. That means the rule for 2 and 3 must work. I need this to make sense. If the rule for 2 works and the rule for 3 works, 6 must go in, because both 2 and 3 go in. Does that make sense? So what kind of number must it be then to be divisible by 6?
Even.
It's got to be an even number where all the digits add up to be
3.
a multiple of 3. Kick ass. Can somebody create a number that does that? Create a number that's divisible by 6. Don't cheat by multiplying something by 6. Create a number, don't say it. Write a number down that is even and all the digits add up to be a multiple of 3. It's a really easy way to do it, but let me see if who's can be.
I got it.
I'll do one.
What's the number be?
Yeah, Jeff. Right? Does that add up to be a multiple of 3?
Yes.
Yes. Is it even?
Yes.
That means it's divisible by 6. What's this divided by 6?
3,
I don't know.
sorry.
Something.
I like the way you started off. I'm like, damn.
Well, because I did it divided by 3.
I think it's 185.
185, yes.
Alright.
1, 3, 3, 2.
Who else has 1? 1, 3, 3, 2.
I did that one myself.
Okay, so that's even. 1 and 7, that's 9. Yes. You guys with me? Yes.
I was doing like bigger numbers, would a number like 12 work?
Yeah, real quick. On this one right here,
Yes.
I love that. It's almost like you're in a head. You're in my head. 1 plus 3 plus 3 plus 2 is 9, correct?
Yes.
It's even and 9 goes in. Therefore, it should be divisible by 18.
Yeah.
What do I get when I divide this by 18? Let's see if that works.
74.
74. There's a very cool idea that's going to come up in a minute. Does everybody sort of get that? I love your question. You're basically saying, can I combine shit to make larger numbers that work? Yes, but you got to be careful. So if I had a number where the last 2 digits were divisible by 4 and all the digits added to be a multiple of 3, 12 would go into it. Yes? 3 and 4 go in, therefore 12 goes in. Are you with me? Okay, now.
7.
I want to show you an example of something. What if I made a number that is even and the last 2 digits are divisible by 4? Does that mean that 8 has to go into it? Let me do this again. So if I made something that 2 will go in and 4 goes in, does that mean that 8 has to go in?
Yeah.
No.
Well,
I'm not trying to trick you. So, real quick. So this does not mean that 8 goes in. Necessarily. It could. And here's why. This is such a cool idea. First off, let's make a problem that actually this works for. Let me see. Give me a second. That'll work. Shoot. What about 116? 116. Is it even?
yeah.
So 2 goes in.
You could have just done 6.
Do the last 2 digits, are they divisible by 4?
Yes.
So 4 goes in. Try to divide that by 8. Doesn't work, correct?
You could
And of course it doesn't work. The only if 2 goes in and if 4 goes in, doesn't 2 go in automatically? No matter what the shit. So here's a really cool idea. This is not just applicable here, and it's one of my favorite phrases in mathematics. I don't know how you feel when I say that. The phrase is relatively prime. So we all know what prime means, yes? Relatively prime means, for example, 2 and 3 are both prime, and they're relatively prime. Because 2 doesn't share any factors with 3. Is 4 prime? 4 is not prime, correct? But 4 and 3 are relatively prime because 4 and 3, do they share any factors besides 1? Does any number go into both besides 1? So they are relatively prime. That is why if I make a number that follows the rule for 4 and a number that follows the rule for 3, 12 will go in. Because the two numbers are relatively prime. Are you guys kind of with me? That's such a beautiful idea. And I really want you to understand, this does not make 8 because if 4 goes in, 2 automatically goes in. It's not new information, so it doesn't make 8 work. But if 3 works and 4 works, that's 2 distinct pieces of information. 12's got to work then. Okay, maybe. I don't know if you guys are really with me. Yes.
So then if 8 goes in, does that mean that 4 and 2 automatically go in?
Oh, sure. If it's divisible by 8, it's automatically divisible by 14. I mean, if it's divisible by 9, it's automatically divisible by 3, correct? So that's true for anything. If something's divisible by 16, is it automatically divisible by 8? Hell yeah. In fact, I know the answer is going to be twice as much when I divide by 8 as it is 16. No, you're fine. No, it's not a stupid question. Yeah.
Does 7 have a rule?
7 has a rule. I haven't looked it up in a while. It's not one that I have memorized. It's a funky ass rule. 11 has a relatively funky ass rule.
Are we looking at
11, yes. I'm gonna have to remind myself because I haven't looked at it in a while, to be honest. Yeah.
There's something about adding the numbers together.
Yeah.
The outside numbers to inside numbers.
Yes. Real quick, we haven't done, no, wait, we've done everything. So 7's got a rule. It's exceptionally weird. And I don't think this book does 7. I know it does 11, but I don't think it does 7.
I remember.
No, it doesn't do 7. Okay.
Teach us 7.
I have to look it up. I can't remember. In fact, 11 I don't. So right now I want to point out, you have to know all the divisibility rules for 2, 3, 4, 5, 6, 8, and 9. I'm not going to make you know 7, and I'm not going to make you know 11. Why not? Because I don't have this memorized. I have all the other ones memorized. So 2, 3, 4, 5, 6, 8, 9. What's the divisibility rule for 1? It's got to be a number, yeah.
It exists.
It exists. Exactly. Now 11, I'm going to look it up. I always forget 11. Oh yeah, oh my god. Sorry. The difference of the sum of the digits whose place values are odd powers of 10 and the sum of, oh my god. Alright, so real quick, watch this. 11 is really kind of nifty. Can somebody do 11 times 11 for me? What is it? Does anyone know what 11 squared is? 121. Somebody do 11 times 11 times 11.
3 times?
Say again?
3 times?
Yes.
3, 2, 1.
1, 3, 3, 1.
Yeah, 1, 3, 3, 1.
He figured it out.
Do 11 times 11. So just take what you just got and multiply by another 11. Multiply that by 11.
1, 4, 6, 4, 1.
Real quick. This is not in the book here, I don't think. I'm still going to show it to you. There's something called Pascal's triangle.
Oh, I've heard of
We
that.
did that last. Yeah. You know
Pedro?
what?
Pedro.
Yeah.
What happened? I never had such a strong reaction. Are you? Is that
I
alright?
like it.
Was it a bad? Did you have to do weird things with it?
Well, yeah, in the last chapter.
Yeah.
Yeah, the last chapter. Okay, good.
We should remember what we do.
So it's just this guy here, right? And you had to do that weird ass thing where you had to find a circle. So you didn't have to construct it, but how do I construct this? What would the next? Does everybody see what the idea? Of course, 1's going the outside.
It'd be 1, 3.
1 plus 2 is 3.
Gonna be 1.
1 plus 3 is 4. 3 plus 3. 3 plus 1.
6, 4.
4.
And then a 1 goes on the outside,
Uh-huh.
Oh, news alert.
Yeah.
right?
Yeah.
1, 3, 3, 1, 1, 2, 1. What's 11 times 1? 11 to the 0 power, or 11 to the first power is 11, and 11 to the 0 power is 1. So this is kind of funkadelic, yes. Okay. There's a lot of other uses for Pascal's triangle besides torturing students. Yeah, but that is one of the main things we use it for. It's a torture device.
Give us 2 examples.
Huh?
2 examples.
Oh, all right. Remember, Mason X. Okay. What's x plus 1 squared? All right, this is a little beyond what we're doing in here, but you all know how to do this, right? Write it twice, right? Careful. Write it twice. X times x.
X squared.
X times 1. 1 times x. 1 times 1. X squared plus 2x plus 1. What are the coefficients?
Oh, wait, what?
What are the coefficients?
1,
1,
2,
2, 1. So if I do x plus 1 to the third power, my coefficients are going to be 1, 3, 3, 1. I have a lot less work to do. I can actually use that. I'm not going to do it right now. That's the most I'm going to do.
This is
Okay?
just an example, right? It's not like.
It's an example of where else Pascal's triangle is useful,
Okay.
besides just torture. So x plus 1 to the 4th power, you could do very quickly. I could then do stuff like 2x minus 7 to whatever power. It gets a little bit weirder, but I can use it. So there's a lot less work to do. Okay, that's enough of that, sorry. The point of this is not Pascal's triangle. That's just a little side note. And I forgot they introduced it last time, but all they made you do was a circle thing, right? If I remember correctly.
What would be the next number? Just out of curiosity.
What do you mean? The next line? All right, so 1 goes in the outside. What's 1 plus 4? 5. 4 and 6? 10. 6 and 4?
Oh, 4 and 6.
Yeah. 6 and 4 is 10. 4 and 1, 5. And then a 1. So this is where it kind of breaks down.
Very quick.
But real quick, what is, can you do in your calculator 11 squared cubed 4 to the 5th power? Out of curiosity.
161,051.
All right, 161, 0, 50? 51?
It breaks,
Yeah.
it breaks down a little.
It does a little bit, but see how that 1 carries over, makes it a 6? The 1 carries over, makes it a 1. And you get 0, 5, 1. It actually is still there, it's just not as clear. Okay, that's definitely more than I wanted to say about that. Okay. So real quick, the rule for 11. Let's do this. Let's do something a little less freaky. What is 11 times 12?
132.
132. What is 11 times 17? 187, yeah. So a cool way to multiply by 11 is 10 plus 1. Right? So if I do 10 times 17 is 170, plus 1 times 17 is 17, I get 187. It's very similar to the rule for 99, right? Yes?
Am I seeing it right? The outside numbers equal the inside numbers?
Well, let's see. What's 11 times, what's 11 times 19?
209?
209. All right, so does that hold?
No.
No. Okay. That's good. That's good. So it's an example of if I don't give you enough information, you can't really get a good pattern from it, right? So the guess was 1 plus 2 is 3, 1 plus 7 is 8. That was a good guess to make, but it breaks down. So what's the actual rule? I got to look at it again.
10.
By the way, if you have your book, it's on page 182.
10 times n plus
11 must divide the difference of the sum of the digits whose place values are odd powers of 10. Holy shit.
Too many words.
I know. Let's look at 187. This is the 10 squared place, yes? 10 to the first, 10 to the zero. Does everybody agree with me?
Yes.
Which numbers are in odd power of 10 place? Which one is in the odd power of 10?
8.
8. So 11 divides, if 11 divides the difference of the sum of the digits whose place values are odd and the sum of the digits whose place values are even. So 8 plus, let me read this again. This is why I don't know the rule for 11. Divides the difference of the sum. Okay, so this would be 8 minus 7 plus 1 is 0. And 0 is trivially divisible by everything. What is 0 divided by just about anything? What's 0 divided by 8? 0. Right? You guys with me? The only number that 0 divided by it is not 0 is 0. 0 divided by 0. It's weird. It's even worse than undefined. It's called indeterminate. Which is a whole other level of shit. Okay. Yes?
Why couldn't they just slap like an imaginary number for that, like they do for when you? take a
Oh,
square
no.
root?
All right, real quick. I thought I showed you this video. Imaginary numbers are real. We didn't just slap them down there. They exist. They just got a bad name. Something divided by 0 being undefined, it actually is more like infinite normally. When I'm talking about like a graph, that's where the asymptote comes from. You with me? So it's not imaginary. It isn't. It's just not a definitive value. It's this idea of it just never gets there. It's just going to infinity, right? So it's not imaginary because imaginary numbers actually exist. This thing doesn't even exist. Okay, maybe. All right, sorry. There's a whole side note. I think that's enough. There's a lot in this section. I think you picked up on that. But the divisibility rules hopefully are pretty straightforward. You do not have to memorize 11 because I don't know if you realized I don't know 11 because I don't like the rule for 11. Sorry, 11. Okay. All right, let's know. Let me know if you have any questions. Otherwise, I will see you Thursday.
I was looking also at the time of the next test.